Okay, our next topic is vectors and statics. So it's chapters 13 and 14. So chapter 13 is the vectors and 14 is the statics. So we'll start off with the vectors. A couple of definitions. So first of all, there's two quantities that we refer to in this context, and one of them is a scalar. And the thing about a scalar, it has size or magnitude only. Alright, so examples of that are distance, time, length, volume, and there's a host of others as well. Alright, so each of those things just have a size. A vector, however, has two things. It has a size and direction. So it has two things there. So examples of that might be 800 metres north, 30 degrees to the east. So that would be a thing we call displacement. Displacement, there we go, which tells you how far and in what direction. So two things. There's other things that have also vectors, so force, velocity, just and acceleration. Examples of things that commonly aren't thought of as vectors. Alright, so how do we represent a vector? We represent vectors, so say for example we've got north, south, east, west, and put that down there like so, and I've got this pointing across here, and that's 45 degrees, and this is a length of say 100 metres. Then that vector that I've drawn, that black line there, represents the vector 100 metres north, 45 degrees to the east. Of course you can use the true bearing. If you use the true bearing, 100 metres 0, 45 degrees T. Either of those. Alright, so basically, what does that mean about it? Well, the length of it represents the 100 metres, that length there, and the other thing, that the angle in here represents its direction, and then we've of course got over here our compass thing so that we know what's going on. Alright, so that's one fairly simple way of doing it. There are other ways, and we can represent vectors as ordered pairs, for example. Okay, so I've got a Cartesian plane like this, and I can draw a vector here. It goes from there to there. Alright, so that's that vector there. And I can also draw one that points in the same direction and is the same length in other places. Okay, so there's some other examples. Now, each of those three things is a vector, and each of those three things on the xy plane here, we're not looking at the coordinates, but the vector itself. In this case, it's 2, 3. So for the vector, and it's not to be confused by the normal Cartesian coordinates. So this tells us here the x component, or x change if you like, and this bit here tells us the y component, or the y change if you like. Alright, so representing vectors like that's not really overly helpful, because like where do they start and where do they finish and all that sort of thing. However, one of these vectors, this one here, is a bit more sensible, because that particular one tells us in relation to an origin, because it's the bottom end of it is at the origin. So it would be much better for these other vectors, so that we know exactly where they are, that we have some reference, and we do have a reference, and that's the origin here, so we can reference the two endpoints of, say, this other one by using those vectors. Alright, so those vectors that I've just drawn in that start down here at the origin, they're what we call position vectors. Alright, so let's clear our drawings. So, position vectors. So, position vectors, they start at the origin. Alright, so position vectors are far more useful. So if we look at the position vector, for example, vector A, which is 3, 1, and if it's a position vector, it starts at the origin, goes 3 in the x, and goes 1 in the y. So this position vector is that there that I've just drawn in the orange, and so that's A itself. Alright, so if I put a point somewhere, let's say down there. Alright, so there's our point down there. That's point B. If I want position vector of B, the position vector for B goes there like so. And how much does it go across this way? It goes across -2. How much does it come down this way? It comes down -4. So its position vector is -2, -4. Alright, so it's much more useful for us to use position vectors. Alright, next. Here's an example. Let's clear all of that. An example. So, if we start at 5 minus 2, where do we end up after our displacement? Of 3, 2. Alright, that's fairly simple really, because we just need to look at our x parts and our y parts, those components in those directions. So it's really just simply a matter of just adding these things together. So you got your 5 plus 3, which is 8, and your -5 plus 2, which is -3, and there it is, that's it. Except I've made a mistake there, it's not -5 here, is it? It's -2 in the question. So -2, not -5. So it's -2 plus 2, which is 0. Alright. Quality of vectors. Alright, vectors are equal. If one magnitude the same, and 2 direction the same. Now your textbook actually has a third one, well, which in my view actually is really just that second one, the direction is the same. Your textbook says that they're parallel, and then the third point is that they point in the same direction, which I believe that number 2 covers that. If the direction's the same, they've got to be parallel, and if the direction's the same, they've got to be pointing in the same direction. So I think that covers both of those things. Okay, so let's look at an example. Righto, so here we've got a whole bunch of vectors over there. So which vectors shown? Are equal. So don't forget, that means that their magnitude, their size, their length has got to be the same, and also the direction is the same. So when you look at that, straight away it looks like F and G are the same. They're both length 2 and they're both pointing straight down. Any others? There, well, if you have a look at the others, you probably find that A and B are the same. Again, their length, they go diagonally across 3 squares and making a 45-degree angle there. Now there is another one that makes 45 degree, that is length the same across 3 squares, and that's H, but the direction of H is different. So it's not equal because their direction is different. C and F and G, well, they're length of 2, but C points up where the other 2 point down, so the direction's not the same. So they're not equal. And even though C and D point in the same direction, their lengths are different, so they're not equal. So that's a quality of vectors. Now, what I haven't done, and I haven't said, that I should have said, is that vectors, when we represent them, there's a number of different ways we can represent a vector. When we're writing it down, we can write it AB like that. That's at the diagram. And we would write that as AB with the arrow across the top. Now that arrow across the top indicates that it's a vector. The other thing we could do is we could assign it a name for the whole lot. Vector A. Now, to say that it's a vector A, this little squiggly line underneath gets used. So A with the squiggly line, that's the same. So either of those ways you can do. Theoretically, you could write this and write that, but they tend not to be overly common. But if you see it, you know what it means. So tendency is when we use the two ends, we put the arrow over the top, and when we just use a single number, we use the squiggle underneath. Alright, so one last example. Okay, so here's an example. An aircraft flies 200 kilometres north and then 400 kilometres east. Draw a diagram and find the displacement of the aircraft. Okay, so first thing we need to do is we need to put a north, south, east, west line on there. Okay, so then we have flies 200 kilometres north. There we are. Then it flies 400 kilometres east. There we are. And we want to know, draw a diagram, find its displacement. So its displacement would be this vector there. Alright, so here's our starting point, here's our finish point. So what do we need? We need to know how long it is. Alright. So we need to know how long it is. That would be a right angle triangle, so our friend Pythagoras, let's call that x. X squared equals 400 squared plus 200 squared. Alright, so when you do that, you get 447.21 kilometres. Now we need an angle in this, and if we use that as the angle, we'll be able to work that out right, because that's between north and it's going towards the east. So if we use opposite over adjacent, which is tan minus 1, 400 over 200, we end up with we end up with 63 degrees and 26 minutes, as maths like to use degrees, minutes. Okay, so that vector then would be 447.21 kilometres north, 63 degrees 26 minutes to the east. Alright, so that's it, set number 1, 13A. See how you go with that.